In this short video, I'm going to give some motivation or intuition, somewhat informal motivation, intuition about what we are going to see in the next video, which is going to be the formal treatment, which relates interlacing and the real-rootedness of polynomials, and what all of this has to do with us wanting to bound the max root of a particular point, polynomial named in the sample space, given a bound on the expectation. Okay, so let's talk about interlacing and real-rootedness. Again, this is a preliminary discussion. It's going to be with theorems but no proofs, and the theorems that we're actually going to use are kind of variants of those, so we are going to prove everything that we will need. This is just an informal discussion, but I think that it's good to have it, because if you're just going to kind of stare or follow me in the actual formal proof, you might not quite get how these ideas came about, and there is a very intuitive way of thinking of these things, so we should see it. Right, so the general plan or the general problem that we are facing is the following. We want to prove something of the sort. We have some n polynomials, capital N polynomials, P1 up to P capital N, and we have a bound on the max root of the expected polynomial, and assuming that all of these polynomials are real-rooted, and that's not followed from that also the expected polynomial is real-rooted. So this is part of the things that we'll have to prove. If you remember, I owed that to you from the previous units, but assume for now that you have these real-rooted polynomials whose expectation, which could be uniform, it could be anything, it doesn't really matter, is also real-rooted. And the polynomials are going to be of degree d. And what we want to prove is something of this sort. We want to prove that for at least one member in this family, the maximum root of that polynomial is bounded from above by the maximum root of the expected polynomial. So the whole game occurs in the coefficient space, right? The expectations and so forth. So if you are looking at degree d polynomials, you should think of each polynomial as a point in the d plus 1 dimension subspace, d plus 1 R to d plus 1, right? So you just look at the coefficient vector, and that's the point that you're going to look at. So we have these points, P1, P2, which are the polynomials, of course, and we have a bound on the maximum root. The maximum root doesn't appear in this picture, but we have a bound on the maximum root of this thing in the middle, so to say, the expected polynomial. And from a bound on that, we want to have a bound on one of these PIs. And so this means that we really need to understand how the max root behaves as a function in this coefficient space. Now, generally speaking, that's a complicated function, as we know. The maximum root is not a nice looking function in terms of the coefficients, but it actually is if you restrict yourselves somehow. So let's see in what sense. So what do we know? So kind of orthogonal to what we said, but it's going to combine back to what we need. So we know that a polynomial has a double root, a multiple root. So a root repeats more than once, exactly when both the polynomial and its derivative are zero at that point. And that you may not know. So there is a way to say when two polynomials have a common root, and in particular when f and f prime have a common root, and that is when the resultant of these two polynomials is 0. So what's the resultant? And again, I stress that you don't really need all of that for the proofs, but it's good to know, and it gives a motivation. So what is the resultant? Well, the resultant of two polynomials is the determinant of some matrix that encodes the coefficients in some way of these polynomials. So if f is this polynomial, and degree n polynomial, and g is this polynomial, degree m polynomial, with the bi's as the coefficients, then you can form this matrix, m plus 1 times n plus 1 matrix, where you kind of put the coefficients of first f and then g in kind of a sliding diagonal fashion, and look at the determinant. Okay, so that's a number. If you walk over a field, that's just an element in the field. In the R or C, we are walking over R, so this is a real number. And the claim is, this claim, it's not so hard to prove, but this claim tells you that F and G in general will have a double root exactly when the determinant is 0. So those are the points where you'll have a common root. So what's important for us is not really the particular form of this determinant or whatever. What we really need to understand from here is that there is a polynomial in the coefficients of F, right? B's are the coefficients of F prime, which are determined by the coefficients of F. So there is a polynomial in the coefficients of F. And when that polynomial is 0, you know that F has a double root, okay? So this 0 set of that polynomial is a manifold. You don't need to, it's enough to have the intuitive notion of a manifold, the 0 set of this one polynomial. And we are going to dub it, I don't know what the name of this thing, but we are going to dub it the double root manifold, because points on that manifold, namely polynomials whose coefficient are zeros of that polynomial, have a double root, right? So what all of this has to do with us? So the point is, and this is an observation, you can make a proof out of it, is that say you are in the coefficient space and you're looking at a particular point, namely a polynomial, and you kind of continuously moving it around, right? Like change the coefficients continuously. And let's say that your starting point is a real-rooted polynomial. So, you're somewhere in space, but that point, if you look at the roots, which are not apparent from the coefficients immediately, but are real-rooted, then if you move around continuously and end up at another point, namely a polynomial, which is not real-rooted, then you must have crossed through that manifold, like moved from one component that the manifold induced to another. You just kind of stumbled across it. Because the only way a real-rooted polynomial will have a complex-rooted polynomial is, first of all, the two real roots has to be like one, and then they go to the complex plane. Okay, so that's what's written here. And let's look at an example that you know when you don't need all the determinants that I was telling you about. Let's look at degree 2 polynomials, for example, just to set the intuition straight. So we know when a degree 2 polynomial has a double root, right? So if the polynomial is this thing, so that's a point in dimension-free space of over R. So if this is the polynomial, then you know that you have a double root exactly when the discriminant is 0. And indeed, once you go below, you get a complex root, and once you go above, you get two roots. So that's what I was telling you about in this particular case. So if you start with a polynomial like a point ABC, whose discriminant b squared minus 4ac is positive, and you end up with a negative value, then it must have crossed for a 0 value, right? And so the manifold, the double root manifold in our case is just this or that if you want to stay with ABC, but if you want to go to XYZ, then it's this manifold, and it's depicted here in this picture from different angles. Right, so all of the points on this manifold are exactly corresponding to polynomials of a double root, and then on one side you will get, I don't know if it's here or here, but on one side you will get real roots, on the other side complex roots, and so forth. What does it has to do with us? It's still kind of seems to be an orthogonal discussion. So here is a fact. It's a theorem. It's not a fact, but I'm going to state it as a fact. Say you have two real-rooted polynomials, and not only they're real-rooted, actually the entire line connecting them, so I think of them as points, so the entire line connecting them, or in terms of polynomials, all of the polynomials of the form alpha f of x plus 1 minus alpha g of x are also real-rooted. Okay, so in that case, if f and g are like that, namely the segment that connects them don't cross the double root manifold, then what you can show is that the max root function is monotone in alpha. Right, so it could be constant, but otherwise it's monotone, increasing or decreasing depending on f and g. So That's kind of great because it tells you how the max root behaves, or it tells you that the max root function behaves nicely where you don't cross the double root manifold. So for example, if we were in a situation where our polynomials, all of our polynomials, P1 up to P5 in this case, are in a single component of the double root manifold, namely none of them, all of the convex combination of them, so all convex combinations don't cross the double root manifold, then we are done. Because, so when you look at this picture and you have a bound on the max root of this polynomial, and you know that on that line, yes, you know that on that line, the function either increases or decreases, or it's constant, maybe depending on direction. So maybe you want to prove an upper bound, and maybe it decreases in this direction, right? So what you can do is you can just look at this point now, namely the point in which that line meets the line connecting P3 and P4, and then again P3 and P4 are on one side of the double root manifold. The segment connecting them don't intersect the manifold. So on that line, the function is decreasing in one of the directions. Maybe it's in this direction. And from there, you can conclude that the max root of P3 is bounded from above by the max root of the expected polynomial. Right, so if all of your polynomials, given the fact, and if under the assumption, which is going to be incorrect, that all of our polynomials, in our case, this is like in factorial many polynomials, are sitting on one side of the manifold, on one component, it's not one side, one component, then we are done by this nice fact. But if you notice, we didn't really use the fact that all of them sits in one side. So here is another example where maybe this is the double root manifold, and you have P1, P2, P3, and P4, and maybe this is the expectation. But then again, it's not the case that P1 and P3 are connected in a line segment, but you don't really need that, right? I mean, since this line doesn't intersect in this example the manifold of double root manifold, then we know that in one of the directions we are going to decrease, so maybe it's direct. And then again, since P1 and P2 don't have the segment containing them does not intersect the manifold, we know that maybe in this direction the max root function is decreasing, and therefore the max root of P2 is also going to be, in this case, bounded by the max root of the expected polynomial. So what I'm saying is that as long as we have this structure of the polynomials, that you can kind of combine them in these line segments in such a way that the line segments never intersect the manifold that we are talking about, then we are fine. We can actually do bound one of the polynomials, the max root of one of the polynomials in terms of the max root of the expected polynomial. Okay, so we are always talking about, the polynomials have some structure and so forth, and so that's the structure that I was alluding to. Now, it turns out that you can express the fact that, we are going to do just that, but instead of talking about this manifold, which is somewhat abstract and unclear, it turns out that using interlacing, you can characterize the fact that a line segment between two polynomial intersect or don't intersect the manifold. And so what we'll be doing is we'll talk in the language of interlacing, but it's really the same thing as saying that the polynomials are in such a configuration. So let me give you the one last fact that, again, I'm not going to use exactly that. I'm going to use a variant of that, which will be more suitable for us, and I'm going to prove that variant. But still, let's see that one as well. So say you have two polynomials, degree D polynomials, say f and g, real polynomials. And I'm going to assume that they are real-rooted. It's kind of implicit, but what follows next, but they are real-rooted. Then saying that, let's start here, actually, in the first one. It's different than what we said before. So say that not only is this line segment connecting F and G is contained in the one component of this manifold, namely doesn't intersect the manifold, the entire line, then in such case, F and G, this is equivalent to saying that F and G interlace in the sense that we talked before. Right, so the interlacing kind of characterizes the fact that the line between the line connecting F and G as 2 points in R to the D plus 1 doesn't intersect the double root manifold. And here there is no reference to this manifold, so it's kind of nicer to work with the interlacing variant of this characterization rather than the manifold one. And saying that the line segment connecting them, F and G, lies in the same component, which is what we will need actually and what we talked about so far, it also has interpretation in terms of interlacing, and it tells us that, so the equivalent condition is that F and G have a common interlacing. Namely, they don't have to interlace one another, but there should be a third polynomial, R of X, that interlace both F and G. Of course, if F and G interlace, then each of them is a common interlacer, but it could be the case that you have a third polynomial that interlace both, while the two polynomials do not interlace. Okay. So in the remaining of what we are going to do, we are going to only talk about in the language of interlacing and not mentioning at all the double root manifold. So that's why I was, it was fine by me not to prove anything in this informal discussion, semi-informal discussion. So what we're going to do next, but let's start it in the next video. We are going to give a formal treatment of real-rootedness and interlacing. So it will have like 6 claims. All of them are quite straightforward, but 6 claims that captures the relation between real-rootedness and interlacing, and they are not going to be quite what I mentioned, something a bit different. And I mean, we also have this extra thing that we need to prove that, and that's the assumption that we kind of assumed here, that the expected characteristic polynomial in our case is also real-rooted. So we'll have more work to do than just talk about bounding the max root, but in the next video, we are going to kind of set the ground and prove 6 claims or lemmas that we are going to use. And then in the last video of this unit, we are going to prove this configuration. I mean, we're not going to talk in this language, but we are going to connect line segments between these 2 polynomials, namely find common interlacings between these polynomials, and then common interlacing between the common interlacings, and so forth, right? Like in this example, maybe. So this is the fact that this whole line segment doesn't cross the double root manifold tells you that this entire line segment is it tells you that P1 and P2 have a common interlacing, which tells you that it is equivalent to saying that the entire segment doesn't cross the manifold. So you can take any point here. That point is not a common interlacing; it's just some convex combination of the two. The common interlacing doesn't appear in this picture, but the existence of such common interlacing guarantees that this line segment doesn't touch the yellow manifold here. And then what we are kind of doing is we look at this polynomial and that polynomial now, and because that polynomial, that line segment connecting the 2 polynomials don't intersect the manifold, it means that these two polynomials, have a common interlacing. Maybe I should have said that these 2 polynomials have a common interlacing, not the common interlacing have a common interlacing, and so forth. So what we're going to do is we're going to kind of construct a system of common interlacing to the polynomials, and then to the convex combinations, and then to their convex combinations, and so forth. And that will be called the interlacing families. So that's the geometric picture that you should have in mind when you're going to see the formal proofs. And I'm quite sure that this will help you digest what will follow.